Welcome to this explainer. Okay, today we're diving into a massive, and I mean literally massive, leap forward in the world of computer vision. We're talking about I-JEPA, which stands for Image-Based Joint-Embedding Predictive Architecture. This was introduced in 2023 by a total powerhouse collaboration. Researchers from Meta AI, McGill University, Mila, and NYU. It completely rethinks how machines learn to process and actually understand visual information. But more importantly, this architecture represents a huge practical step toward Yann LeCun's broader vision of advanced joint embedding architectures. It is this brilliant, elegant solution to one of the most stubborn bottlenecks in all of artificial intelligence. So let's dive right in and see exactly how it works.
So think about this for a second. How does an AI actually learn to see when absolutely no one is feeding it the answers? Natural language processing basically solved this years ago with masked language modeling. Hiding words in a sentence and forcing the model to guess them based on context. But trying to translate that self-supervised success over to computer vision, that has been a historical nightmare. Because images aren't neat little discrete tokens like words. They are continuous, dense, and super redundant. Finding a way to train visual models without relying on massive datasets of human-labeled images has been the holy grail here. Previous attempts to adapt masking to images were notoriously inefficient, and that is exactly the core limitation that I-JEPA was built to finally overcome.
Here is our roadmap for today. Section 1, Meet I-JEPA. Section 2, Pixels versus Meaning. Section 3, Inside the Architecture. Section 4, The Training Process. And finally, Section 5, Real-World Applications. All right, let's jump right into Section 1, Meet I-JEPA and the world of self-supervised learning. Before getting into the mechanics, we really need to focus on this fundamental shift between pixel space representations and semantic space embeddings. So, what is an embedding? In this context, an embedding is a highly compressed mathematical representation that captures the core meaning, the semantics of an image, while deliberately ignoring all those low-level, high-frequency details. It abstracts away the raw noise. And I-JEPA's primary innovation isn't just generating these embeddings, it's that it moves the actual prediction target entirely into the semantic space. By completely bypassing the need to predict raw pixels, the model is forced to understand overarching concepts rather than just memorizing local textures.
Moving on to Section 2, Pixels versus Meaning, a whole new paradigm.
You see, older self-supervised methods, like masked autoencoders, basically played a giant game of fill-in-the-blank. They'd blank out parts of an image and ask the model to reconstruct the exact missing pixels. Honestly, that approach is just computationally wasteful. It forces the model to use massive parameter counts and immense computing power just to learn high-frequency details. I'm talking about the micro-variations in the bark of a tree or the exact texture of a patch of grass. Details that are totally irrelevant if you just want to know, hey, is this a tree? Furthermore, those old methods required heavy image augmentations, like randomly cropping, flipping, or aggressively altering color channels just to keep the model from overfitting. Well, I-JEPA throws that old playbook right out the window. It doesn't predict missing pixels, it predicts hidden embeddings. It requires zero heavy augmentations. It focuses entirely on meaning, not the math of the pixels, which saves an immense amount of computational resources.
Okay, Section 3. Let's look inside the architecture, which is entirely Vision Transformer-based. The whole framework is powered by the Vision Transformer architecture, and it's carefully split into 3 distinct components. Let's use a detective analogy because it really helps clarify how they interact. First up is the context encoder. This is our detective at the crime scene, looking only at the visible clues, the unmasked patches of the image, and extracting feature representations. Then we have the predictor. The predictor takes those clues and tries to guess the full story, predicting the representations of the hidden regions. And crucially, it uses a narrow, lightweight vision transformer to do this guessing, which is absolutely key to the system's efficiency. Finally, we have the target encoder. Think of this guy as the omniscient narrator. It processes the complete, unmasked image to produce the true target representations that our predictor is actively trying to match. Now, you might be wondering why this specific 3-part setup. Well, it's totally necessary to solve a notorious issue called representation collapse. Basically, if a joint embedding model isn't constrained, it will eventually realize that the laziest, easiest way to minimize its error is to just output the exact same generic embedding for every single image it sees. Traditional models, like SimCLR or MoCo, avoid this by using contrastive learning. But contrastive learning is incredibly expensive. You have to process massive batches of negative pairs, forcing the model to calculate how different one image is from thousands of others all at once. I-JEPA avoids representation collapse entirely without needing a single negative example. Pulling this off without contrastive pairs is a huge architectural flex, and it drastically cuts down on memory overhead.
Let's look at Section 4, the training process, and specifically multi-block masking.
So how does it actually learn? The spatial logic of I-JEPA relies on a very clever multi-block masking strategy. Several image regions, usually 4 of them, are randomly selected as target blocks to be hidden. And these are intentionally big, often covering 15 to 20% of the total image each. Then, a single expansive context block is selected. But here is the critical rule. Any parts of the context block that overlap with the hidden target blocks are completely removed. By cutting out this overlap, the architecture rigorously forces the model into long-range spatial reasoning. Basically, it completely removes the AI's ability to cheat by just copying adjacent pixels. It actually demands genuine understanding.
The training loop executes this strategy step by step. Step 1, divide the image into patches, define the context block, and mask out those target blocks. Step 2, the context encoder processes the visible patches to extract the features. Step 3, that lightweight predictor takes those features and tries to guess the semantic embeddings of the hidden blocks. Step 4, compare and update. The predictor's guesses get compared against the true embeddings from the target encoder. Now, the context encoder and the predictor update normally through backpropagation, but the target encoder, it is not updated via backpropagation. It uses a stop gradient operation, meaning gradients literally do not flow back through it. Instead, its weights get updated using what's called an exponential moving average of the context encoder's weights. This specific mathematical choice is exactly what keeps the whole architecture stable, prevents the targets from degenerating, and ultimately stops that representation collapse we talked about earlier.
Which brings us to Section 5, real-world applications, because versatile features are what we're really after.
Once pre-training is completely finished, the framework undergoes a big transformation for deployment. The predictor and the target encoder, they are completely discarded, just thrown out. What remains is only the context encoder. Because we've dropped those other components, the resulting model is incredibly lightweight, which is a massive win for developers trying to reduce deployment overhead. You just feed any new image into the standalone encoder, and it efficiently spits out a robust, global image embedding that captures the semantic reality of that image. And armed with that rich global embedding, you can attach a simple task-specific layer, like a linear classifier, and get remarkable results across a huge variety of downstream tasks. It handles standard image classification flawlessly. It excels in few-shot and semi-supervised environments where you barely have any labeled data. It seamlessly transfers what it's learned to entirely new, specialized data sets. It can even handle complex stuff like object counting and depth estimation. To put this all into perspective, I-JEPA hits state-of-the-art linear evaluation numbers on massive data sets like ImageNet, and it does so using only a fraction of the compute required by previous top-tier models.
Ultimately, because I-JEPA is predicting image representations instead of individual pixels, it is just remarkably more computationally efficient, and it consistently learns more meaningful visual features. By skipping the heavy lifting of pixel-by-pixel reconstruction and avoiding all those aggressive data augmentations, the model trains significantly faster, demands way less compute, and gives you a vastly richer, more generalized understanding of whatever visual input you throw at it.
So here's a thought to leave you with. If frameworks like I-JEPA can successfully learn the deep semantic architecture of our visual world totally on their own, completely bypassing human labels and brute force pixel reconstruction, what will they learn to understand next? As this highly efficient joint embedding approach inevitably expands outward into complex video analysis, multimodal audio, and beyond, the trajectory of self-supervised AI is about to accelerate dramatically. Thanks so much for joining me on this explainer, and I hope this provided a deep, clear look into the mechanics of a truly groundbreaking architecture.